Number 82. Nichrome wire is used in some radiative heaters. Letter A. Find the resistance needed if the average power output is to be 1 kilowatt utilizing 120 volts of alternating current. Alright, so we have to find a relationship between watts, or aka power, voltage, and resistance. So what's the relationship? Power is equal to voltage squared divided by the resistance. So if we have to solve this for resistance, just do a simple little cross multiplication. And we realize that resistance is equal to voltage squared divided by power. All we have to now do is plug in the values. And the power they told us is 1 kilowatt. Be careful there. You have to convert that into watts, so just multiply that by 10 to the 3. So when we do this in the calculator, so it's going to be 120 squared divided by 1 times 10 to the third. And we get a value of about 14.4. So 14.4 ohms. All right. How about now letter B? So letter B is saying what length of nichrome wire having a cross-sectional area of 5 squared millimeters is needed if the operating temperature is 500 degrees Celsius. All right. So what we need to do is we need to find the length. And we know we're talking about square area and all this stuff. So we're probably going to use the formula that the resistance will equal the resistivity of the material multiplied by the length divided by the area. Remember, resistivity is sensitive to temperature, or in other words, the resistivity of the material will change as the temperature changes. So what we now need to do is we now need to solve this for L, all right, the length, and let's see then what we get. So when we solve it for L, we're going to cross multiply the A on out of that denominator and across into the numerator. Cross multiply that resistivity. So now a division, and here's now the formula, okay? Cross-sectional area times resistance divided by resistivity will be equal to then the length. So what we now need to realize is that we're trying to find it the length at its operating temperature. Now the operating temperature then, if we want to find the length here at operating temperature, we have to know the cross-sectional area at the operating temperature, which actually might change, by the way, but we're going to assume it doesn't. And the operating temperature, the operating resistivity at the appropriate temperature. So when you look up the resistivity in the book, it tells you the resistivity at 20 degrees Celsius. So what we realize here is that I'm going to write something like, let's call this the final resistivity, and we'll call this like the initial, okay? So let me get rid of that circle. Let's call that initial. And we might have to now do a substitution. In other words, we're probably going to have to substitute this formula down here, the resistivity, in for this final value, okay? Remember, this kind of represents final resistivity. We've done practice like that. So what I'm going to do, reorganize this a little bit. Cross-sectional area multiplied by resistance, all divided now by the original resistivity, or the resistivity at 20 degrees Celsius, multiplied by 1 plus then my alpha value, right? And the alpha value is going to be 0.4 times 10 to the minus 3. So we got 0.4. Actually, let me just substitute everything in and then I'll plug it in. And then multiplied by the change in temperature. Sorry. Now let's plug everything in. So the cross-sectional area they told us is 5 squared millimeters, but we need that in meters. So take 5, multiply it by then 10 raised to the minus 3. That would have gotten us to meters, but then you got to square it because we're dealing with squared millimeters. Multiply that now by the resistance, right? So the resistance here is what we found in the first part. We're assuming that, this is the resistance when the the radiative heater is at operating conditions, okay? So 14.4. Divide that then by the initial resistivity, which is the 100 times 10 to the minus 8. Multiplied by then 1 plus our alpha value. That's also got from the book. So 0.4 for nichrome, 0.4 times 10 to the minus 3. And then multiply that by now the change in temperature. So it's always final minus initial, right? So the final, we're talking about at 500 degrees Celsius. The initial then was at 20. So it's just going to be 500 minus 20, trailing off there. But I think we get the idea. So now we're going to plug everything on into the calculator. So it's going to be 5 times 10 raised to the negative 3. Square that now. Okay, 1 second. Cool. Multiply that by then 14.4. We get an answer of about 7.2 times 10 to the minus 5 for the numerator. So now what we're going to do is we're going to now do the denominator. So in parentheses, 100 times 10 to the minus 8 times, parenthesis again, 1 plus 0.4 times 10 to the minus 3 times, and you can do parentheses again if you like, but you can also do the math in your head. 500 minus 20 is going to be 480. So just multiply that by 480. Close the parenthesis, and we get a value of about 60.4. Okay, so the length here is going to be about 60.4 meters. That's the length. All right, so that's how long of a piece we're going to need. And finally, letter C, it says, what power will it draw when first switched on? So the power it will draw when it's first switched on will be equal to the voltage applied squared divided by the initial resistance. Okay, so the resistance we calculate over here is not initial. This we're assuming is at the operating temperature. So what we need to do is we have to find, and remember this is the operating temperature is at 500 degrees Celsius. So we have to calculate the initial resistance here, basically at 20 degrees Celsius. All right, we're going to assume that this thing is starting at room temperature, which is about 20. So, whole bunch of assumptions all over the place. So power is going to equal the voltage. So that's 120 volts squared. That ain't changing. That's what's coming out of the wall. And then divided now by the initial resistance. But we know, take a look at the bottom right-hand side. We know that the initial resistance here would be equal to then the final resistance, which we found, divided then by this whole term. Okay? So I'm doing, hopefully that algebra is okay. I'm just solving this for the initial resistance. Then I'm going to plug in the result down here for the bottom. And I'll even change the color to make it hopefully a little clearer. So we're going to do RF over, remember this thing is RF, over then 1 plus alpha times the change in temperature. Okay? So that's what I need to do. So I'm going to do the math in the upper left now. So power will be equal to 120 volts squared divided by the final, which we said that's basically the operating, right? Resistance, so 14.4, all divided by now 1 plus my alpha value of 0.4 times 10 to the minus 3, multiplied by then the change in temperature, right? So the final value here is going to be the 500. The initial is going to be 20, so it's the same kind of idea. And this fraction looks a little funky, but, take this numerator and then divide it by this whole thing on the bottom, okay? And that's how we're going to get our answer. So the power is equal to 1. So I'm going to simplify the bottom first, all right? I'm going to actually do the 1 plus 0.4 times 10 to the minus 3, multiply that then by 480. Then what I'm going to do, I get a value of about 1.2-ish. Then I'm going to take 14.4, I'm going to divide it by that value, so then I get about 12. And then I'm going to take 120 squared, and then I'm going to divide it then by the 12 value. So it comes out to be about 1192. Right, so the power here is going to be equal to about, 1,190 watts. Okay, you need that in kilowatts, you know what to do. So there it is. Thank you guys very much. Hopefully this helps. Please remember to subscribe. We'll see you soon. Take care.